Right, hi everyone. So, another video, this time on trigonometry, and I know you've done quite a bit in GCSE, but unfortunately, like Easter Bunny and Santa Claus and all that, chemistry and biology, it's all been a lie. You've been lied to the whole time. A bit harsh, I'll give you time to absorb that fact. Uh, but this whole Sokotoa business, it's just a lie. It's not a, it's not a truth because yes, sine, cos, and tan do describe um, the proportion of the opposite over hypotenuse, adjacent over hypotenuse, but it's not actually the opposite over hypotenuse at all. And this is what you see with this circle here. Okay, this is a circle with equation x squared plus y squared is 4. Okay, so the radius is 2. I could use any circle. X squared plus y squared is 1, say. That's called the unit circle because the radius is 1 and it's centered at the origin. I could use any circle to display the point. But what I've got is this point here, this point P with coordinates x, y, and I've got this angle, which you'll see is 0.6435. That's radians, okay? Remember that we know what radians are now. There are 2 pi, lots of radians in a circle, okay? Now, we might know what the graphs of sine and cos are, but not necessarily why they look like they do. And that's what this is about. We're gonna show you, or we're gonna derive why they look like they do. I mean, why, if sine is opposite over hypotenuse, why can sine be negative? Makes no sense. Opposite over hypotenuse, they're both distances. So of course, they can't be negative. But of course they can if sine describes the y-coordinate over the radius. This is the radius. This is the y-coordinate, which acts as your opposite, if we're talking about right angle triangle. But y is movable as it goes round a circle, round the edge of a circle, okay? The y-coordinate can be negative, so therefore sine can be negative, because sine is the y-coordinate over the length, the radius, just as cos theta is the x-coordinate, the adjacent over the radius, and tan theta is your opposite, which is your y-coordinate over your x-coordinate, okay? If we understand that, then we can start to show how the graphs are actually formed. So we're going to show how sine is formed. And we're going to use this axis. I'm going to draw it on the axis as we go, and we'll see how close I get to. So this is my angle in radians axis. So let's start going for it. We're saying sine theta is y over r. So I'm going to start doing this. So sine of the angle displayed there, 0.6435, is the same as its y-coordinate. Its y-coordinate's down here, 0.6435 at the moment, all over 2. It's too late in the day for me to be doing mental maths. I don't do that stuff anymore. 6435 divided by 2, 0.34175. Okay. That's my proportion. So if the x-axis is my angle axis, 0.64 is about, I don't know, there, and 0.34 then is going to be about there-ish. Okay, let's carry on round our circle then. So if I go round a bit more, this time pi by 3, so 1.159. Let's try that. So sine 1.159 is the y-coordinate, which is 1.833, sorry, over 2. So 1.833 over 2. So that's 0.9165. So 1.159, what's that about there? And 0.9165, what's that like? About there. Okay, this is looking good. Let's keep going. So I'm going to move around the circle a little bit more. So let's go for pi by 2. Pi by 2, my calculator, is 0.157. So sine of 1.57 equals my y coordinate, which is 2 over 2, which is 1. So at 1.57, what's that about there? This is 1. Cool. Let's keep moving round. The computer does something a bit dodgy here. It's giving us the shortest, the smallest angle between the x-axis and the radius. So we'll have to do pi subtract our angle displayed here. So let's make it a bit more obvious. 1.159. So pi subtract 1.159. So actually the angle I've gone round is 1.98. So let's look at that. So sine of 1.98 is the same as our y coordinate, which is 1.833 over 2, which we just found out was 0.9165. That's interesting. Let's start dotting that down then. So 1.98, that's about there, and that gives us there. That's good. Okay, let's keep going round. So we do a couple more. So let's go around a bit further this time. So 0.3176, so pi minus 0.3176. This angle actually all the way round is 2.824. So sine of 2.824. 2.824 is about there. And that gives me a y coordinate of 0.6245 divided by 2, then divide by that radius. 6245 divided by 2. And we've got 0.31225. So my proportion 0.3125 is about there. Okay, cool, looking good. Now let's start moving the circle around even more. Okay, here we go. So now we're at this point here. So I've got to do something. I've got to do, again, it's doing the shortest angle, so pi plus 0.5451 this time. Hopefully you're getting why I have to do that. It's just some weird glitch with the computer. So 3.59 radians. So sine of 3.95 radians is the y coordinate, which is minus 0.8718 this time over 2. There's your reason why we get a minus. So 0.8718 divided by 2. So this is 0.4359. So this time we're 3.95 round, which is about there, and we're 0.435 down, so that's going to be about there. So notice now we're below the x-axis. Let's do a bit more. So I'm going to go all the way around this time. So again, that's found the shortest distance, so I'm going to have to do 2 pi. So pi plus pi by 2. Sorry, 2 pi subtract 0.9273. So the whole angle I've gone round here is 5.3559. So sine of 5.399, 5.3559 is that y coordinate, which we know is minus 1.6 divided by 2 is minus 0.8. So 5.3 is about there, and our y coordinate was minus 0.8, which is about there. Okay, let's see if I've done a good job or not. Now I'm going to put the actual graph on top. So if I put in y equals sine x, let's see. Oh, yeah. Fantastic. Fantastic. You see how the dots have lined up? See how the dots have pretty much bang on? Really happy with that. Awesome. Yes. Okay, cool. So that's how the sine graph was produced. Now note what happened. Okay, in this circle, within this quarter of the circle, every single value of sine, every proportion of sine was positive, wasn't it? Okay? Sine was positive here, wasn't it? Between 0 and 90 degrees, all my y values are positive for sine. Okay, so at the moment, I'll draw it a bit more obvious. Here's our sine graph, okay? And this is pi by 2, this is pi, this is 3 pi by 2, this is 2 pi, yeah? And as we keep going round the circle, if I kept going round the circle, this thing, this proportion, would go on forever, okay? This is why sine has a period of 2 pi, or 360 degrees. So a period means how often does it repeat itself? It repeats itself every 360 degrees. If we did it for cos, cos also repeats itself every 360 degrees, okay, or 2 pi, right? So you can see that the y values, here's the y goes between 1 and minus 1, right? You can see that in between 0 and 90, between 0 and pi over 2, sine is always positive. So this would be called the positive quadrant, okay, the first quadrant. In this second quadrant, between 90 and 180, or pi by 2 and pi, sine is still positive. The y-coordinate is still positive. Whereas here, you can see that as I go round, this is my angle between pi and 3 pi by 2 is negative. So this is negative here. And for here, my y-coordinate is negative, right? So sine is always positive between 0 and 180 degrees. And every multiple of that, as we go round, so it's positive here, it's positive here, it's positive here. Do you see? So every 2 pi, you'll have the same pattern going along. That's good. Now this is called the cast method. So some classes are going to use graph method. To solve problems, we're going to use cast. Okay? So cast, exactly what I just did then. Okay? For a circle, as the point moves around the circle with radius r and there's your angle, okay, sine is positive here. Sine gives positive, sine is positive, sine is negative, sine is negative. If we took the graph of cos, so if I did the same thing, which I'm not going to do because that took a while, okay, but I'm showing you how it all worked. So you should know what these graphs look like. So that was sine. This is cos, and cos x is simply a translation of sine, isn't it? It's just moved along by 90. So you can see here, if we use the same quadrant results for cos theta, right, or cos x, between 0 and pi by 2, cos is positive. So if I go back to my thing, cos in green, positive here. Between pi by 2 and pi though, cos gives a negative y value. Negative y. So here, cos is negative. If we go around again, pi to 3 pi by 2, so 270 degrees, cos is still negative. So negative. And if you keep going up to here, between 3 pi by 2 and pi, cos is positive again. You see, the y value is positive. You can do exactly what I did in terms of the unit circle to find out why that is. If you just took your x-coordinate and divide it by the radius, yeah, you could do exactly the same thing. And we could also do the same for tan. What's the tan graph? So y equals tan. Remember, tan is y over x. So you can see here between 0 and 180, or 0 and pi by 2 radians, where there's an asymptote. We'll talk about why that is, right? Tan is positive, okay? Between pi by 2 and 3 pi by 2, tan is negative. Between 3 pi by 2 and pi, and 2 pi, sorry. Oh, sorry, where are we? Hang on. 0 pi by 2, pi 3 pi by 2 and 2 pi, sorry. So between, let's do that again, between 0 and pi by 2, tan is positive. So let me do it in a different color, red. So tan, positive. So they are all positive in this quadrant between 0 and 90. Tan between pi by 2 and pi is negative. So pi by 2 and pi is here. So tan is negative. Between pi and 3 pi by 2, tan gives a positive y value. So positive. And for the last one, again, between 3 pi by 2 and 2 pi, tan is negative. So can you see, all are positive here. Only sine is positive here. Only tan is positive here, and only cos is positive here. See? Cast method. Alright? It's really important we understand how this works and why we have infinitely long graphs, because this point P can just keep spiraling around the circle, just keep moving around the circle, moving around the circle, moving around the circle, and the proportion will forever be the same no matter how many times the angles go round. If the angle is here, you go around 360, your point's back where it started again, okay? So you can see that the period for sine, so the period for sine is 360 degrees or 2 pi. For cos, it's also 360 degrees or 2 pi. For tan, it repeats itself every 180 degrees or pi radians, okay? There we go. That's what sine, cos, and tan are. That's how their graphs were made. The two big identities that we can glean from this is simple. Since sine theta is y over r, since cos theta is x over r, since tan theta is y over x, we can start building two big identities which you're going to massively need later. So one of the identities which you might know is sine squared plus cos squared is 1. But why is that? So sine squared theta is y squared over r squared if I square both sides. Cos squared theta, therefore, is x squared over r squared. So if we add these together, sine squared plus cos squared theta, we get sine squared is y squared over r squared, plus cos squared, which is x squared over r squared. Same denominator, means I can put them together. But what is x squared plus y squared? Remember, this comes from the circle. The circle here, this is my r, isn't it? This is my y coordinate and this is my x coordinate. R, you know from Pythagoras, x squared plus y squared is r squared, isn't it? Right? So x squared plus y squared is r squared. All over r squared is 1. So sine squared theta plus cos squared theta is always equal to 1. That's what those three lines mean. That means always equals 2. Okay? Always equals 2. This is called an identity. And you're going to need this a lot. Identity number 2, another big one, involves tan. To prove that tan theta is the same as sine theta over cos theta. Well, let's do that. So tan is y over x, isn't it? We know that sine theta is y over r. So therefore, if we want to get y by itself, times up by r, y equals r sine theta. We know that cos theta is x over r. So if we times up by r cos theta must equal x. So therefore, since tan theta is y over x, but y is r sine theta, and x is r cos theta. So therefore, tan is sine over cos. And there are some constraints on this, but for now we'll leave it at that. So there's your second identity, okay? Big identities that you'll be using all of the time, and really important. Okay, I think we'll leave that video there then.